Imagine standing in the middle of a power substation. It's a place humming with invisible energy, a critical node in the vast network that keeps our lights on. The air crackles with a low, persistent buzz. Giant gray oil-filled transformers stand like silent sentinels, their cooling fins giving them a ribbed, industrial look. These are the workhorses of the grid. Their job is to step voltage up or down. Overhead, a complex web of high-voltage transmission lines stretches out to the horizon, carrying immense electrical power from generating stations. These lines converge here, terminating at massive ceramic insulators that prevent the powerful electricity from shorting to the ground. These transformers don't just work in isolation. They are part of a highly controlled system. Nearby, you'll see rows of circuit breakers and disconnect switches, ready to isolate a part of the grid in a fraction of a second if something goes wrong. A small control building houses the brains of the operation. Inside, walls are lined with control panels covered in meters, blinking lights, and complex diagrams called mimic panels. These panels show engineers the real-time status of every single component in the yard. It is here that the intricate details, like how transformers are internally connected, become incredibly important for the stability and safety of the entire power system. The sheer scale is impressive, but the magic is in the details, deep inside the transformers themselves. How do we ensure that, when we connect these powerful devices together, they work in harmony? If you connect two transformers incorrectly, the consequences can be catastrophic, leading to massive short-circuit currents and widespread blackouts. This is where a hidden language comes into play, a code that tells engineers precisely how the windings inside each transformer are configured. This code ensures that multiple transformers can operate in parallel, sharing the load seamlessly and reliably. It's a fundamental concept that underpins the reliability of modern power grids. This secret language is known as the transformer vector group. It's a shorthand notation that describes the winding configuration and the phase relationship between the high voltage and low voltage sides. Think of it as a compatibility label. Before connecting two transformers, engineers must check this label. If the vector groups don't match, they simply cannot be connected. Understanding this concept is not just academic. It is a crucial piece of practical knowledge for anyone working with electrical power systems. It's what separates a stable, functioning grid from a chaotic and dangerous one. So, what exactly is a vector group? Let's start with the basics. A three-phase transformer has two sets of windings, a primary, high-voltage winding, and a secondary, low-voltage winding. Each of these sets can be connected in one of two main ways: delta, symbolized by a D or D, or star, also called Y, symbolized by a Y or Y. A delta connection looks like a triangle, connecting the windings end to end. A star connection brings one end of each of the three windings to a common point, called the neutral, which can then be connected to the ground. The vector group designation tells us two key things. First, it tells us the connection type for both the high voltage and low voltage windings. For instance, a DIN transformer means the high voltage side is delta connected, and the low voltage side is star connected with its neutral point brought out and typically grounded. The capital D signifies the high voltage side, and the lowercase y signifies the low voltage side. The N indicates that the neutral point of the star winding is accessible. This seemingly simple combination of letters already provides a wealth of information about the transformer's internal construction. But there's more to it than just the connection type. The vector group also includes a number, and this is where it gets really interesting. This number represents the phase shift or time difference between the high voltage and low voltage voltages. We represent this using a clock face analogy. The voltage vector of the high voltage winding is always imagined to be pointing to 12 o'clock. It's our fixed reference point. The number in the vector group then tells us where the low voltage winding's voltage vector is pointing on that same clock face. Each hour on the clock represents a 30-degree phase shift. So, for a transformer with the vector group Dyn11, we know a few things. The high voltage winding is delta. The low voltage winding is star with a neutral, and the number 11 tells us the low voltage vector is at the 11 o'clock position. Since the high voltage vector is at 12 o'clock, there's a 1 hour difference. This means the low voltage waveform lags behind the high voltage waveform by 1 hour times 30 degrees per hour, which equals 30 degrees. This 30-degree lag is a fundamental characteristic of this transformer type, and it's a critical piece of information for system engineers. Let's visualize this 30-degree lag for Dyn11. Imagine two spinning hands on a clock. The longer, red hand represents the high voltage phasor, and we fix it permanently at the 12 o'clock position. Now, the shorter, blue hand represents the low voltage phasor. For a Dyn11 transformer, this blue hand points to 11 o'clock. The angle between the two hands, measured from the leading vector, which is the high voltage at 12, clockwise to the lagging vector, which is the low voltage at 11, is 330 degrees. However, the convention is to measure the smaller angle, so we say the low voltage lags the high voltage by 30 degrees. This phase shift isn't arbitrary. It's a direct result of how the windings are physically connected. The delta connection on the high voltage side links the phases in a loop, from A to B, B to C, and C to A. The star connection on the low voltage side connects one end of each phase winding to a common neutral point. The specific way the phases on the low voltage side are connected relative to the phases on the high voltage side determines whether you get a Dyn11 configuration or something different, like a Dyn1, where the low voltage lags by 30 degrees but in the opposite direction, essentially leading by 330 degrees. One of the most significant advantages of the Dyn11 configuration is how it handles certain undesirable electrical phenomena, specifically zero-sequence currents. These currents appear during faults between a phase and the ground. In a star-connected system, the neutral point provides a path for these fault currents to flow to the earth, which allows protection systems to detect the fault and trip the circuit breaker. This is a crucial safety feature. The delta winding on the high voltage side provides a unique benefit here. It traps third harmonic currents, which are a form of electrical noise, and circulates them within its closed loop, preventing them from propagating back into the high voltage network. So, the full Dyn11 label is a concise summary of these features. Delta means a delta connection on the high voltage side, which is great for trapping harmonics. Star means a star connection on the low voltage side, providing a useful neutral point. The N explicitly states this neutral is available, essential for grounding and protecting against earth faults. And 11 defines the specific 30-degree phase lag between the primary and secondary voltages, which is vital for connecting transformers in parallel. Each part of this simple code conveys a critical piece of engineering information. The preference for the Dyn11 vector group in distribution systems isn't just a matter of tradition, it's based on solid technical advantages. Firstly, the availability of a stable neutral on the low voltage star side is a massive benefit. This neutral can be solidly grounded, providing excellent protection against earth faults. It also allows for the supply of single-phase loads, which is how most residential and commercial customers are connected. You can tap between one phase and the neutral to get a lower voltage, making the transformer incredibly versatile for distribution networks. Secondly, the delta winding on the high voltage side acts as a natural filter for third harmonic currents. These harmonics are generated by non-linear loads, like modern electronics, and can cause overheating and interference. The delta winding effectively traps these problematic currents, allowing them to circulate within its triangular connection without polluting the upstream high-voltage network. This harmonic suppression leads to better power quality and improved efficiency for the entire system. It's like having a built-in cleaning crew for your electrical supply. The 30-degree phase shift is also crucial for parallel operation. To connect two transformers in parallel, they must have the same voltage ratio, impedance, and critically, the same vector group. If you try to connect a Dyn11 transformer in parallel with a Dyn1 transformer, even though their winding connections are similar, their phase shifts are different. The low voltage of the Dyn1 would be at 1 o'clock, while the Dyn11 is at 11 o'clock. This creates a massive 60-degree phase difference between their secondary terminals, leading to a large circulating current that would damage or destroy the transformers. Walk into almost any 33 by 11 kilovolt distribution substation, especially across India, Europe, and many other parts of the world, and you will find the Dyn11 vector group specified on the transformer nameplate. This configuration provides the perfect balance of features: a neutral for grounding and single-phase loads on the low-voltage side, harmonic suppression from the high-voltage delta winding, and a standardized phase shift for parallel operation. For these reasons, Dyn11 has become the de facto standard, the most widely used and trusted transformer vector group in medium-voltage power distribution systems worldwide, ensuring our power is both reliable and safe.